Sharon will talk about high performance, high concurrency Ruby in UringMachine. Please welcome him.
Cześć wszystkim. Mam na imię Sharon. Bardzo się cieszę, że tu z wami jestem. I love the Polish language. It has a very beautiful sound. It's very sexy, I find. So, hello everybody, my name is Sharon, and today I would like to talk to you about UringMachine and building concurrent Ruby apps with fibers and IO Uring. So, let's talk about fibers. What is a fiber? A fiber is simply a context of execution that can be suspended and resumed. And in Ruby, for each thread, we start with a single context of execution, which we can refer to as the main or the default fiber. And we can create additional fibers or context of execution that we can switch between, such as so that one fiber will be suspended and the other will be resumed. Now, fibers have many different uses. In Ruby, for example, they are used to implement lazy enumerators. They can also be used to implement state machines, parsers, and such stuff. But today we are going to concentrate on their usage for concurrency. And fibers are useful for concurrency in very specific circumstances, especially when we're dealing with applications that are I/O bound. So we'll go back to this idea of I/O bound applications as we progress through this talk. So let's look at how we work with fibers in order to achieve concurrency. Now, the program that we see here does two things at the same time. One task is to read from standard in and to print back the data that we read to the terminal. And the other task is to sleep for 5 seconds and to print the message to the terminal. So we start by creating two fibers. And for each fiber, we provide a block of code that will be run in the context of the fiber. Now, when we create a fiber, the fiber is in a suspended state. So when we get to the end of this program and we have created the two fibers, in order to start those fibers running, we call reader transfer to switch to the first fiber, the reader fiber. And this has the effect of suspending the main fiber, which ran up until that point, and to resume the reader fiber. So what the reader fiber does is, since we do not want to block the thread while we are reading from standard in, we call read non-block, which will not block. Instead, if there is no data available, we are going to get a wait-readable return value. And in that case, we are going to call sleeper.transfer, which will switch to the sleeper fiber. And the sleeper fiber will do something similar. It also runs in a loop, and it just checks if enough time has passed since it started running. If not, it will transfer control back to the reader fiber. So what this program will do is that it will ping-pong between those two fibers until a condition has been met and the relevant fiber can continue processing. So one problem that we can see in this code is that the references for the fibers are hardwired in the code. So the two fibers actually need to know about each other. But what happens if we wanted to add a third fiber that ran concurrently at the same time? Or what happens if we want to be able to create fibers dynamically as we go? So a solution to that would be to introduce the concept of a run queue. The run queue is simply a queue that holds fibers that are ready to run. So instead of calling reader transfer or slipper transfer, we are going to abstract it away into a method called fiber switch. And in that method, we are going to add the current fiber to the tail of the run queue and pull the fiber at the head of the run queue and switch to that fiber. So it has the effect of doing the same thing, but it is mediated through the run queue, and that allows us to create a solution that is more universal. Now, a second problem with this program is that all of that ping pong between the two fibers is a lot of busy work for nothing, basically. So maybe instead of polling all the time for a condition to be met, we can use some of the tools that the Ruby runtime gives us in order to wait for an I operation to complete. So instead of doing all those loops and checking for the I operation, the completion of the I operation, we, excuse me. So instead of this loop that we had, that was a bit of an ugly code, we abstract it away into a single method call. And you can see now that the code in the fibers, the two fibers, it's not only shorter, it also shows a much clearer intent of what it needs to do. So from the point of view of the fibers, we're just doing a normal method call. It's obviously blocking, but we have hidden away the whole mechanism of switching between fibers. And one peculiar thing about the do-read and the do-sleep methods is that actually we are not doing any I/O. Instead, we are registering the intent to perform I/O, and we just do a fiber switch. So here we have the whole solution for creating an alternative I/O implementation that is fiber aware. And we see that in the fiber switch method, instead of always putting the current fiber into the tail of the run queue, we just pull fibers off the run queue, resume them, and when the run queue is empty, it's only then that we are going to perform the I/O. And when we do the I/O, we use io.select to check for readiness, which will block the thread. But since we have no more processing to do, there's no problem with that. And when we actually read the data from standard in, we can then put the fiber back on the run queue and then return to processing the fibers normally. So one thing to observe about this technique of concurrency is that actually when the run queue is not empty, excuse me, I need some air. So when the run queue is not empty, that means that we have more CPU-bound work to do. We have more processing to do. And in contrast, when the run queue is finally empty, that means that we have no more work to do, and we can then go and wait for I/O operations to complete. So we will have CPU-bound work and then I/O work, and it's going to alternate like that. So now let's talk about I/O Uring. So, excuse me, I have no air. So I/O Uring is an interface for performing asynchronous I/O. It is a Linux-specific interface. It doesn't exist on other operating systems. It provides a comprehensive set of I/O operations that follows the design of the normal system call I/O API. And it does so, it provides asynchronous I.O. by breaking each I.O. operation into 3 phases: submission, execution, and completion. So let's look at how we interact with I.O. Uring. With I.O. Uring, an application sets up 2 circular buffers, or ring buffers, hence the name I.O. Uring, I.O. user ring. The first buffer is a submission queue, or SQ. The second buffer is the completion queue. And the way we perform I.O. is that the application adds entries to the submission queue. Each entry describes an I.O. operation. The kernel pulls these entries from the submission queue, performs the I.O. asynchronously. Meanwhile, the application can do other stuff, and eventually, when each I.O. operation is complete, the kernel is going to put entries, completion entries, into the completion queue, which will eventually be read by the application and processed by the application. So, in this example that we see here, this is some C code. We start by setting up the I.O. Uring instance, and we then, in order to submit an I.O. operation, we get a pointer to an entry in the submission queue by using I.O. Uring get SQE. We prepare the entry using one of the I.O. Uring prep functions, in this case a read operation. We provide the different arguments for the read operation, which is really similar to how you would do it with a normal read syscall. And we also set a user data that is associated with the SQE, with this I.O. operation. Now, the user data can be a tag, it can be an ID, it can be a pointer to some C data structure. And this value will be copied by the kernel into the completion entry once the I.O. operation is completed. And this will allow us to identify the I.O. operation that we're dealing with. So we prepare the SQE, and then we call I.O. Uring submit. This is actually a wrapper around a system call called I.O. Uring enter. And this lets the kernel know that there are entries that are waiting to be processed by the kernel. Meanwhile, while the kernel is performing the I.O. operation, we can do some more processing, we can submit more I.O. operations, and eventually, when we are ready, we go and we wait for one or more CQEs to be available on the completion queue. We can then look at the user data of the completion queue that allows us to identify the I.O. operation, and we can process the result of the I.O. operation. So you see here that there is a pattern that is actually very similar to the concurrency model that we saw with fibers. We process whatever work that we have to do, CPU-bound work, we submit I.O. operations that we are interested in performing, and eventually, when we have no more processing to do, then we can wait for one or more CQE's completion entries to be available, and we can process them. So, what if we wanted to combine the two? What if we wanted to drive the fiber concurrency model with I.O. Uring? So here's a sketch of how this could look. We have a sleep function, a do sleep function, that prepares an SQE. It also keeps track of the current fiber in order to know which fiber originated the I.O. operation. And then we do simply a fiber switch. The fiber switch function implementation is very similar to what we saw before. We pick fibers off the run queue, we resume them, and finally, when the run queue is empty, we can then go and submit all of the SQEs that we prepared and wait for one or more completion. And for each CQE we process, we grab the fiber that is associated with the I.O. operation and we put it back on the run queue. So this is basically the design behind UringMachine. UringMachine is a project that I've been working on for the last year or so, and it is an implementation of fiber concurrency based on IO-Uring. So in UringMachine, the idea is that a machine is an instance of IO-Uring plus a run queue. It has different methods for controlling the lifetime of fibers, and it provides a low-level API that follows more or less the normal system call IO interface. We work with raw file descriptors, and we also work with buffers that the application is supposed to provide for these method calls. UringMachine also includes some higher level abstractions over this low level API, namely the UringMachine IO class, which it does buffered reads, which we'll discuss later, and also a fiber scheduler implementation that we'll also look at. So to recap, the UringMachine concurrency model combines the idea of a run queue with the IO-Uring submission queue and completion queue. UringMachine also supports canceling IO operations. IO-Uring has a mechanism for canceling ongoing IO operations. So in UringMachine, whenever you want to cancel an operation, you can manually schedule the fiber that is currently blocked on an IO operation. You can manually schedule it with an exception. And when the fiber is finally resumed, it detects that the IO operation has not completed. It will cancel the IO operation at the level of IO-Uring, and it will finally raise the exception that was scheduled with the fiber. There's also a universal mechanism for timeout, and since error handling follows the Ruby exception, the standard Ruby exception mechanisms, it is very easy to implement patterns such as graceful shutdown. UringMachine also supports using multi-shot operations. So IO-Uring has a few different operations that are multi-shot variants of the normal operations, namely for accept, for timeouts, for reads, and for receives. So the way this works is that normally with IO-Uring, you submit an SQE once and you receive a completion once. But with multi-shot operations, you submit once and you receive multiple completions. So for example, with accept, the normal way to do it would be to submit and accept and wait for a completion, and then submit and accept again and wait for a completion. Instead, with multi-shot accept, we submit once, and the kernel will just provide us with a continuous stream of completions, each completion with the FD of the new connection. So the way this looks to the developer using this interface is with an accept each method that will run as an infinite loop. And on each CQE that arrives, the fiber will be resumed and it will yield the value to the block that was given to the method call. The same for periodic timeout that can be used for implementing repeated tasks that you want to perform periodically. And also there is the possibility to perform multi-shot read and receive, but that also requires the use of another feature of IO-Uring called provided buffers. Let's look at that feature. Now, the idea behind provided buffers is that for multi-shot reads and multi-shot receives, there's a problem because normally when you do a read, you need to provide some kind of buffer, a pointer to a location in memory where the data will be read into. But what happens if you want to read repeatedly? So that is what provided buffers are for. So the way this works is that the application sets up another circular buffer called a buffer ring, and this buffer holds entries that each entry references a buffer for reading that the application has allocated. So the application is basically saying to the kernel, here's a set of buffers, you can use them. With each CQE, tell me which buffer you used and how much data you read into it. And in recent versions of the kernel, IOUring is able to consume buffers incrementally, such that, for example, if you provide a buffer that is 16 kilobytes in size, if you only read 3 bytes, then the kernel will only consume 3 bytes from the buffer. And the next time it reads data, it will put the data where it left off. And the best thing about this feature is that you can use the same set of buffers for as many concurrent read operations as you want. So there is no need to allocate buffers separately for each read operation. You can use the same set of buffers for all your reading. So what UringMachine does is it builds on this feature of provided buffers and on multi-shot operations to implement completely automatic buffer management. So the way this works is that UringMachine allocates a bunch of buffers and it provides them to the kernel. And as CQEs arrive, it will track also where data was read for each CQE, and it also tracks the amount of buffer space that is left for the use. If that buffer space falls below a certain threshold, it will allocate additional buffers and provide them to the kernel. And in that way, we avoid allocating buffers for each read operation. We just use the same set of buffers over and over again, and buffers can be recycled back and provided back to the kernel once we are done consuming them. So in addition to the normal way of reading with either single-shot reads or multi-shot reads, we can also have a higher level abstraction called the UringMachine I/O class, which builds on top of those primitives. So buffered reads are important when we are implementing protocol. In the Ruby world, we take it for granted because the I/O class is so convenient to use and provides all those features that we don't even think about them. But if, for example, we need to read a whole line, if we're dealing with a line-based protocol, or if we need to be able to read a set of a fixed size, of a message of a fixed size, actually, when we read using the low-level API, we are not guaranteed that we'll get a complete message. The message can arrive in chunks, since TCP sockets is basically a stream of bytes. We are not guaranteed that we are going to get the whole message. So we might have to repeat the read and meanwhile put the data that we already read in a buffer. So the idea behind the I/O class is that we build on the fact that we receive CQEs continuously and that they use a set of buffers that we provided to the kernel, and the kernel reads incrementally into those buffers. So the I/O class provides an API that is very convenient to use for implementing protocols. And let's see how that works. So as we receive CQEs, those CQEs are translated into segments. Segments are just little C data structures that reference chunks of data that are that the kernel read into the buffers we provided to it. We then arrange those segments in a linked list, and that can give us the whole message that we are waiting for. So in that way, we have a segmented buffer. It's not a contiguous buffer, but we avoid copying data, and we also avoid allocating and reallocating buffers. Another feature that UringMachine has is a fiber scheduler implementation. So the fiber scheduler interface was introduced to Ruby in version 3.0, I believe, by Samuel Williams. He's the guy behind a lot of the work on fibers in Ruby in the last 2 years. And the idea of the fiber scheduler interface is to provide hooks in the Ruby I/O implementation such that in the presence of a fiber scheduler, when we are performing I/O, instead of the I/O being performed by the Ruby runtime, it will be deferred to the fiber scheduler, which will be able to perform those I/O operations in a fiber-aware way without blocking the thread. And this provides compatibility with basically the entire Ruby ecosystem. Currently, there are a few implementations of fiber scheduler, of the fiber scheduler interface, and most notably the async gem, and it's actually a family of gems that are authored by Samuel. He's also the author of the Falcon web server that was discussed already in other talks, and now there's also UringMachine. Some more features that I'll discuss briefly. There are some synchronization primitives, mutexes, queues, which use the futex version in the IO Uring version of futexes. There's also some SSL integration. So the OpenSSL gem uses the OpenSSL library, and the OpenSSL library has this concept of a BIO, basic IO, I believe, which is the method that is actually used to perform sending and receiving of encrypted data. But what happens in the OpenSSL gem is that it uses the standard Ruby APIs only for checking for readiness, but the actual sending and receiving is done by the OpenSSL library, which will do it using normal system calls. So if we want to do the sending and receiving using IO Uring, we have to override the BIO with a custom BIO. So the UringMachine gem does just like that. I also contributed a PR to the OpenSSL gem itself. It stays open. There is a competing PR from one of the maintainers of the OpenSSL gem, and hopefully this will be adopted. One of those PRs will be adopted in the future. There's also support for SSL in the IO class, such that you can implement protocols on top of SSL sockets. UringMachine also includes support for some Linux-specific interfaces, such as PID-FD, for working with processes using FDs instead of PIDs, and the iNotify interface for watching file system events. And now, the moment you've all been waiting for, because you've probably been asking yourself how fast it is, and the answer is, it depends. However, what you see in this chart here is a certain scenario. It's a synthetic scenario. In this scenario, we create 50 pipes, Unix pipes, and we create for each pipe a pair of threads or fibers one for reading, one for writing, and we are reading and writing data a certain number of times, and we measure the time it takes. So the blue bar is the thread implementation. The red bar is the async fiber scheduler implementation. The orange bar is the UringMachine fiber scheduler implementation, and the green bar is the UringMachine low-level API implementation. So you can see the difference between the different implementations. Another thing to note is that as we increase the level of concurrency, we also increase the advantage that UringMachine has compared to threads. Now, I should add that this is a very specific scenario where we are doing basically only I/O-bound work. But in real life, this will not happen. In real life, you will have also a lot of CPU-bound work. This is especially true for any mature Rails application, where you are going to do a lot of allocation of objects, a lot of copying of data, a lot of rendering of templates, etc. I recommend for you all to read the mythical I/O-bound Rails app by Jean Boussier, which goes into a lot of detail in discussing this. So, what can you do with UringMachine? Well, for the time being, not much. There is a proof of concept rack-compatible web server that I worked on for a few days, just as to show that it can run Rails applications, but it probably will need a lot of work in order to be able to use it in production. There is a project called Syntropy, which is my own web framework for my personal use. That is maybe the subject for another talk. I'm working on a closed source platform for dealing with time series data for one of my clients, and I'm also I'm going to convert some legacy apps that I maintain from using Event Machine to UringMachine. So, what lies in the future for UringMachine? There are some missing features that I want to add to it, most notably support for IPv6 addresses. I also want to come up with some kind of DSL for batch processing, such that instead of having to create a separate fiber for each concurrent I/O operation, we could just say to UringMachine, here's a bunch of files, go and read them, and let me know when you're done. So this is also an idea that I need to develop further. Another thing that I want to do is to implement protocols on top of the UringMachine I/O abstraction, which, as we saw, is about buffered reads. So there is already an implementation of the Redis protocol that is working very nicely. And I want to do the same for HTTP1, HTTP2, and if I get to do this for PostgreSQL, the PostgreSQL wire protocol, it will be really awesome. And I also want to be able to integrate UringMachine with, let's say, the pillars of the Ruby ecosystem, Rails, and Hanami, and Sidekick, and other projects like that. So that's it. Życie jest piękne. Life is beautiful. Thank you for listening.
Thank you very much, Sharon. Are there any questions?
On the multi-shot except for listening socket, aren't we concerned there that we commit to way too many in-flight TCP connections? Is there any kind of way to limit that we do not have like 100,000 TCP sockets open in the end and run out of file descriptors?
I believe you can set the size of the backlog using the listen call.
Sure, but if I do that, but I on the slide I saw like I can delegate accepting to the kernel, and the kernel will keep accepting and giving me like 100,000 active TCP connections. That's what I understood at that point. Even if I set the backlog to one times 100,000 is still 100,000 active FDs.
I'm not sure.
Cool.
I don't know.
I'm just curious. So okay,
yeah,
thank you.
This needs to be investigated.
Any other questions?
Thanks for the talk. So are you already using Falcon like everywhere with your framework and with other stuff?
Falcon,
Yeah.
in the web server, I don't use Falcon.
So what are you using? You said that you have your own rack and then your own framework. And how you do
The framework that I wrote for myself, Syntropy, runs on top of a custom-made web server that I created that runs on top of
So that would be another talk.
It doesn't use Falcon.
All right.
Yeah, thanks for the talk again. And I'm interested in what were the original business needs that forced you to implement such an approach? Like, what can be the example that tells you that probably you should think about optimizing this exactly part of the application?
Yeah, so actually I've been working with fibers and with our Uring for a few years already. I already published some gems that attempt to bring IO Uring to Ruby. There was one gem called Polyphony that was very, very high level with all kinds of other features for concurrency. There was another gem that was much, much lower level. So UringMachine for me was really about finding the correct level of abstraction such that on the one hand we will not have to deal with the internals of IO Uring, but on the other hand we could build higher level abstractions on top of it. And in the work that I do, I work in process control, in industrial process control. And I have a few applications that are based on event machine. Now, event machine is... how many people here know what event machine is? Right, a good number. So for those who don't know, event machine is an event reactor for Ruby. It was quite popular back in the day when people were looking for a way to create reactive applications in Ruby, when Rails was just breaking into the scene. But unfortunately, event machine has been unmaintained for quite a few years already. So I was, and I'm still am, a bit concerned about this. And since the apps that I'm maintaining, that I am responsible for, they are already running for many years, and they are seeing all the time. They have to scale more and all that. This was a concern for me. So UringMachine, even the name, I mean, it basically came from wanting to find a replacement for event machine.
Okay, yes, that's clear. Thank you so much.
Okay, I see no more questions. Correct me if I'm wrong. No. Thank you very much, Sharon.
Thank you.